Hi everyone. I'm Artur Bergman at Crucially on Twitter. Is the audio okay? Okay. I'm the founder and CEO of Fastly, and I used to be at Wikia and Sixpart, and I have a long history of building very large websites very early on. So, quick warning, I do run a CDN. I'm still a little bit unused to this entire being a vendor and talker at the same time, but I'm trying not to be too much of a vendor. Velocity has a lot of history for me. A couple of years, many years ago now, I guess, at Oscon together with Steve Souders, Jesse Robbins, and John Olspo is where we convinced O'Reilly to actually put Velocity on. And now we're here in New York, which is exciting. And I kind of think of Velocity as, speed, and what we do is to make shit fast. And so this talk is a bit of what that is about. So why are things slow? And the reason why things are slow is latency. To be fast, you need, see, that's really annoying. Latency is really, 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 really annoying. It is the mind killer, and it makes people bored. And when people are bored, they leave your site or your program or app or whatever. So latency is a measure of time delay experienced in a system, the precise definition of which depends on the system and the time being measured. In communications, the lower limit of latency is determined by the medium being used for communications. So latency, in a much simpler way of putting it, is you're waiting for shit. Right? Like every time you see something spin, it's latency. I suffered horrible latency on the flight over from London yesterday, where my average ping time for the entire flight was 2.5 seconds to Google. You could really tell who had good implementations of their websites when you're behind 2.5 seconds of latency. So it brings total obliteration to your performance, right? It just completely kills everything you have. Now, the key here is that it's actually possible to beat it. But, and what I'm trying to get through for this talk is, you need to look at it holistically, continuously, and never ever give up, right? It is too easy to ignore. So unless you employ people or that actually focus on latency as part of their job, you're not. At Fastly, we have a couple of us, and they keep beating me up for forgetting it. And latency builds up over time. So a good example is hard drives. So this is New York, and I haven't done this in New York before. How many people here still use hard drives? Holy crap. Like, seriously? They need to do like a little side 2.5-minute rant about why you're wasting your lives? Okay. Anyone of you using hard drives care to tell me why you're using them? Really? In what dimensions are they cheap? Small New England college. They're cheap if you're storing data you're never going to access. If you're storing data that you actually want to access more than an average of 120 times per second per unit of data that you're storing on a hard drive, they're actually costing you more than SSDs, right? Because then you can't use the full aspect of, or the full storage of the machine, of the hard drive. So SSDs basically solve most of the latency problems that I'm talking about, and you could ignore the rest of my talk. So go buy them. Like, who still has them in their laptops? At least that should be no one in here. Do you like the spinning wheel of latency? But then you go down to CPUs. So Intel does wonderful, wonderful, wonderful CPUs. They've saved us from having to do a lot of re-engineering over the last couple of years by continuously beating our expectations of their inability to actually deliver anything. Sadly, most people waste that by running horribly inefficient software. But even on CPUs, there is something called, the SSE42 has a string instruction that executes in one cycle. It's really cool. You can give it 16 bytes against another 16 bytes, and it does a full crossbar comparison of those two 16 bytes and gives you back a bit index. You can do regular expression, and you can do index off and a bunch of other things. And it gives you that back as a bit index into another register. But it takes 8 cycles to get the result, right? So you have latency even at that level. Like 8 cycles is pretty fast compared to most of the stack we run, but it still limits, you still have to think about it when you code. In human life, it takes forever to go to the DMV in California. I don't know about here. Or I assume everyone uses AWS S3, basically. And this is your latency. So one of the nice things about being a CDN is seeing all the traffic to S3, or sad thing about being a CDN, I guess, maybe. So this is actually measured out of Ashburn, Virginia. So we're about 2 milliseconds from the S3 termination server here. And that percentile was over 4 seconds. Right? So if you try to build any serious app on that, you have to build in latency constraints that can handle a 4-second spike. And that's all internal to S3. There's no network there. That brings networks. So it's about 75 milliseconds from here to San Francisco. And the reason for that is that constant. Right? So we go back to the medium. The definition had the medium of transport. That's the speed of light. It's about that in fiber. It's about that many miles per second. And the best case each way is 25 milliseconds. And then we add about a shitty network gear in between and non-optimal routing via Chicago and Denver. And you end up with about 75 milliseconds from here to San Francisco. So when you write code, either it runs on the client or on the server. Like latency on the network is probably the biggest form of latency you're going to deal with. And there's this wonderful list of fallacies of distributed computing, which I saw someone tweet that it printed them up in their office. You probably should. And one of them is that latency is 0. And when you start thinking about the kind of web apps that we write today, the distributed system that we're developing actually extends all the way out to the web browser, right? Like the web browser doesn't have a single one clean HTTP request and is done. It's actually part of the entire system throughout. And one can kind of, jokingly say, but if Facebook pushed a piece of execution code out to all the people that are connected to Facebook at any given time, that's probably the world's largest supercomputer, right? That is continuously communicating between all those edge nodes through their central nodes and then back out, which is a very, very, very large distributed computer that extends far beyond where most people think that the limits of distributed computing goes. So at Fastly, we have kind of the worst condition for a distributed system, right? And we try to work against some pretty hard deadlines on when we want to deliver content and how we want it to go. One thing that gives some context to what we do, but also is a side note, it's an important lesson, is when you approach a problem, one of the best ways of succeeding is by reducing your constraints, right? If you don't need to do X, then you can get away without a whole bunch of things. So as a CDN, we can lose customer data, right? That's what a cache does. When it gets full, it throws it away. That's what memcache does. So it's the same as if you engineer a system that relies on memcache never losing data, you haven't really engineered a system. Same with a CDN. And I'm ignoring the origin story here. So that allows us to relax certain constraints. Or if you think about it as a database, we don't need to be ACID on anything except the delete. So at Fastly, we have very much come to realize that the network is not reliable. The internet is a highly unreliable place where split brain happens pretty much continuously. And if you know BGP and you watch the routes change, you can see that. Also, it is a system where latency is not zero. You travel far and you notice that. You travel onto your 3G network and you notice that. Bandwidth is not infinite. It's not infinite in your data center or on the internet for that matter. One of the great things that I think people don't look seriously enough on web page test is the little thing that says how saturated the pipe is. Right? You can have a business need to push down 2 megs on each request to a customer. The question is, how are you saturating that pipe? Because there's a maximum bounded, if the customer can only pull 1.5 megabit per second, it will take a certain amount of seconds to push down 2 megs. But are you doing it as efficiently as possible? And for everyone who does push down 2 megs per page view, I paid $2 for each page view when I was flying yesterday. So thank you for those efficient sites. It's very enlightening to have a bandwidth counter that costs you money next to your surfing. Was eye-opening. And then on a macro scale, it turns out when you go to an ISP and say, hey, I want to buy a terabit, they don't go, here, have a terabit. They go, why? What are you going to do with it? Who are you going to send the traffic to? When are you going to send the traffic? No, you can't do that. No, we don't have that. No, we'll have to dig, right? Like the internet is not infinite, and one number is that I think peak capacity in the U.S. is probably somewhere around 40 terabits or something. If we want to deliver 1080p streams to all of the U.S. to replace TV, we need something about between 4,000 and 6,000 terabits of capacity in the US only, right? There is a lot of bandwidth. There's a lot more needed. The network is secure is patently not true. Topology doesn't change. Try that. So one of the best MTRs or trace routes I ever seen was 4 hops. It was London, 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 where the second and third hop was 300 milliseconds. Anyone want to guess what that is? So my first thought was congestion. And then I was like, seriously, any router that keeps a packet around for 300 milliseconds, probably so congested it's already dead. Thankfully, I knew the person on the other side, so he did a reverse trace route. And this is really important when you're debugging networks, is the reverse path. The reverse path literally went around the world. And I couldn't see that on my trace route, but they could definitely see it. There are many administrators of the internet. There are many administrators of the tools of the internet. There are many, you can say that about the browsers. There are many different browsers. There are many different servers. They never really work together. In fact, they rarely work together well. And on the doesn't work well together, it is a very, very diverse network, which is good, because otherwise it would fail way more often. So, for example, there was a Juniper bug that a Zimbabwean ISP put a community string in that crashed a whole ton of Juniper routers. Thankfully, we're not only based on Juniper routers on the internet. We have many. And that is a good thing, but it creates interesting challenges. So the internet has gotten much better over the last 14, 15, 20, 30 years, ever since it started. It continues to get better, don't get me wrong. But it's still bound by speed of light and by the fact that it's pretty lawless. We are apparently hiring. So come help us solve some of these things. And it's full of people like Netflix who don't give a fuck that they're abusing, your bandwidth. If anyone from Netflix is here, I love you. Though you blocked me when I was overseas last time. But, they go and buy bandwidth, and because there isn't enough bandwidth, some pipe somewhere gets flooded, right? And suddenly your performance hurts, and you don't know why. And I'm picking on Netflix mainly because they keep saying that they're 35% of the internet, so it's pretty easy to blame them. But it's also not their fault, right? It's the entire chain, the entire stack that needs to adapt. And the internet is lawless. Like, the DDoSes are pretty freaking horrible. The attacks are continuous. And you have to deal with that. And then from the browser side, you have to deal with getting attacked and faked and spoofed and SSL and all of that shit. And that's pretty much a full-time thing. And all of those countermeasures that you do, if you aren't careful, or rather, they will definitely affect your latency. And if you aren't careful, they will kill it. Right? So who here uses active firewalls? Really? No one is willing to admit that they're using a session tracking firewall? So I'm sure one of you are. But since no one is, I can't really rant about it, which is sad. But it's an example of where state doesn't work on the internet. You use a stateful load balancer. You guys learn quickly not to admit things. Ah, there are a couple there. Congratulations. You also got a choke point for DDoS. And anything that keeps state on the internet, anything that keeps state on any massive set of data, usually will affect latency very, very poorly. So you want to be stateless and non-sticky. So the OpenFlow comment is, I don't know, who uses OpenFlow here? Thank God. So open one flow in OpenFlow takes about 9 milliseconds for each new flow you want to add to the table. To go back to the controller, which is typically written in Java, which has a stop-of-the-world garbage collection problem, which is supposed to control all your switches. That is a lot of crack smoking. And then, so just quickly go through, evolution of a fastly pop. So many years ago, roughly around the same time as the first Velocity, is when I actually started the origins of Fastly. And I flew with 2 servers to the UK as checked luggage. It was a great way to get things through customs if you don't get caught. If you do get caught, you smile and say, And fun fact, you have to be present when TSA opens the box and opens your machine and looks inside it. I'm not sure what you think they'll find, but. So our first generation was 2 machines in a rack with multiple direct ISP uplinks and 20 gigs of capacity and 50,000 RPS. They didn't really scale very well, mostly because of the multiple direct ISP uplinks. So each ISP was plugged in directly. And that made it hard to go beyond 2 servers. So we added an Arista switch. And well, side note, since I don't work for them, I can plug them. Who uses Aristas here? Okay, more of you should. They're freaking awesome. You do this, you log into them, and you type enable, and then you type bash, and then you have a full Red Hat system. If you do get them, you can talk to Vlad and get his Ganglia packages that puts all of the stats directly into Ganglia, directly off the Arista, which is really, really awesome. And then you have a full Python API to change everything on the forwarding base. There's actually another little side rant about switches here. Switches are like awesome, and they're completely killed by our current vendors. And I hope to spend more time exploring something that has the capacity to do about 600 million regular expressions per second on a 128-byte window of a packet can actually do, because that's what a $1,250 chip from Intel can do, right? And all we have is this crappy Cisco Junos shit on top of it. So we added, OpenStack was a way to get event from shitty vendor software because and it was taken over by shitty vendor software. And in fact, every time you hear someone say software-defined something, what it actually means is trying to get away from shitty software that vendors provide. That's how you expand that statement, right? Like servers, storage, network has always been fucking defined by software, not by hardware. There's no code in the hardware. It's software that drives it. So we added Keep Alive, D, and VRP, and that worked, but was pretty fragile. So we added a third machine, and we could get more performance in a reliable fashion. And who here has used extensive amounts of keep alive D or VRP? It doesn't scale very well. I don't know why I'm surprised whenever I discover that things don't scale, but it turns out they don't. So we started using something called ECMP. ECMP is wonderful. Equal cost multipathing, you basically hash the flow based on certain parameters, and the flow stays persistent through the system. And that turned out to be much more simple and is completely stateless. So then we decided to go a little bit bigger. So we had the 3 racks in a ring. We added each ISP into each location. We had a loop. We had no machine to internet over subscription. You kind of look in our architecture that looked a bit like this. Right? So 3 Aristas, 20, 20, 20 between them, and each of them have 80 to the internet. And this is a very, very small example of how data centers don't really work well today, which is it doesn't fucking work because the interlinks between the switches is smaller than the total aggregate bandwidth outbound, or total aggregate bandwidth needed in case one of those breaks, right? You have 80 that you need to push in over 2 20s. And then you add spanning tree to that, and you only get one of those 2 20s. Or you add VXLAN, in which case you're going to cry. Or you add NVGRE, in which case I don't even know what that means. Or Trill, which exists on the chips, but not in software. And this is the east-west bandwidth problem, right? When you grow, especially when you start adding things like Hadoop or just too many servers, I've seen this with web servers with memcache backends, where they need, and then you add another cage somewhere else, and now you have an east-west bandwidth problem. And as soon as those memcache packets start dropping, well, you're fucked, right? And it also, increases risk for split brain, which is really bad inside a data center. And I know we should design for it, and I know everyone who uses AWS has to design for it, but generally I like to design for my data centers to not be in split brain versus assuming that they are at all times. And then there's this magic thing called quality of service. So if you deploy quality of service at any point in your architecture, you've basically given up. Unless you can define a form of traffic or a form of interaction that you do not actually care about, right? So if, you have some shopping system that you only care when people do certain things and you're willing to drop all other traffic, then QoS works. On the network layer, if you have a particular form of traffic you don't care about, then QoS works. So my ISP in San Francisco is WebPass, have decided to QoS everything down that's not port 80 or port 4 for free. So what this means is that I can watch 10 or 5 1080p streams, but I cannot keep an SSH session open, which is pretty frustrating. And at line rate, like if you actually saturate your systems, QoS just means that you're never going to keep up. At 40 gigabits per second, you have 5 nanoseconds or 6 nanoseconds per packet to do something. There's no place to buffer, right? It's like 4 gigs per second of data coming in. Like if you can only process 4 and you start falling behind, you will not catch up. The only place where I can see internally on, either if, and this applies on the application level too, right? Like if you can only process 1,000 transactions per second, then QSing some of them down is not going to help, because if you go over 1,000, you're going to fall behind. So QS means dropping. That's all it means. So it's really the reverse of quality of service. The only place I can see that is if you have vital control plane functions that if they go down, you can't actually do anything, in which case it's probably a good idea to prioritize those over anything else. And it's probably a good idea to deprioritize any traffic coming out of China. So we use commodity machines. These machines are awesome. You can pretty much take one of these and put like 1,000 VMs in it and call it a day. 768 gigs of RAM is an interesting problem to work with, because suddenly scanning memory incurs latency. Like scanning 768 gigs of RAM actually takes a fair amount of time. But anyway, I know this is somewhat a stretch of a commodity system, but it is a commodity system. There is nothing magic in there. It's just large amounts of it, right? And then we put 16 of these in a rack, and we plug them into 4 different switches, and we don't oversubscribe, so there's 16 ports per switch for the machines and 16 for the upstream. And so each machine can cache about 2 billion objects, do about 40,000 requests per second, and push 25 gigs. So if you add that together, you get 12 TB of RAM, 288 TBs of SSDs, 16 billion objects, and 400 gigabits of usable capacity out of one rack. Like, you can actually do that. That is fully possible. So that takes your east-west bandwidth problems to a new level, right? Like, we don't have 100 gig Ethernet, or we do, but it's barely coming. And 600,000 requests. And what we did to avoid the east-west problem, right, is to basically plug all machines in that need to speak to each other into each switch, so they always only have one switch to jump between 2 machines. And we can then use 64-port machines, so we can actually put 2 of these together for a pretty terrifying 24 TB of RAM per machine, or 1.1 terabits of internet facing capacity. And part of me someday wants to send a SYN flood from one of these pops, probably aimed at China. So, spine networking. Who uses spine networking here? If you use any of the clouds, you definitely do spine networking. So you basically used to have these huge chassis. They incurred a lot of latency and they sucked. So you move to a method where you have the same way that we did, where each machine that needs to speak to another machine is on the same rack. You basically make it so that each switch that needs to speak to any other switch is only one switch away with multiple links. And you use this thing called ECMP to load traffic evenly between them. And the reason why you need to use it consistent ECMP is because you need one flow to always stay on one path, or you'll get out of order transmissions. So we can put 4 of these machines together for 4 terabit of capacity. And actually, Trident 2 chipsets just came out that have 96 10 gig ports and 8 40s per 2U, which means that we could put enough of these 2 rack units together to get 18 terabits from one location, with every machine having full bisect bandwidth to every other machine in the pop, which is pretty crazy. And if you want one of these 2-unit boxes, we can build them for you. So one of the best things, but the easiest wins, right, is to use someone like us to deliver content on the internet, because we take care of that problem. The real benefit is, of course, caching. But even if you don't cache content, just terminating at the edge helps tremendously, like usually somewhere between 40 and 50%. And the reason for that is we go back to latency, and we go back to medium, and we have this thing in TCP called slow start, where a connection only grows to a certain bandwidth product over a certain amount of time. And if you have servers at the edge that can keep long-running connections open to origin, well, that bandwidth product of maximum transmission is going to be really high. So we, for example, see this with S3. So getting shit earlier, now I'll go on some cred. We've had connections open to S3 that have been open for days. Like one TCP connection, like 25 million downloaded objects, open for like a couple of days, right? And always at full TCP speed. So once the objects start flowing, you don't have to wait for the ACKs to come back. And this is especially even more important when it comes to SSL, because TCP is one handshake plus the request. SSL is handshake plus SSL handshake, or session resumption plus worst case a second handshake, and then the actual requests. And so if you're 200 milliseconds from the server, you incur that before you can even start talking. When you're close to it with a long-running connection, you basically avoid that. It's also known as DSA by some vendors is technically just CDN without caching. But the real benefit is, like, can you actually cache content on the edge? And if you can, then you win. So we'll skip that one. Another takeaway is computers are state machines, right? And you can program them. And ultimately, they execute assembly. So don't be afraid to use that, right? Like, so when we do our virtual host matching, we used to have some fancy code that did it. It was slow. It was using 25% of our C code. So we're based on Varnish. Varnish allows you to embed C code. You can embed assembly in C code, which means you can embed assembly in a Varnish config file. And this is a very small snippet of the virtual host matching code we have that on my laptop can do about 400 million virtual host lookups per second without any memory allocation or deallocation, and cut our CPU usage by about 30% across the board. So an example of where caching is really useful. I don't think Mark is in the talk, but so machine customers are a very specific form of customers that have very precise clocks. And people love their cron jobs, and they don't know what display means. So we host this little site called raw.github.com. And you will see 2-second spikes. So this is another great example of why 2-second or a second resolution stats are important, right? If on a 1-minute chart or a worst case 5-minute chart, you won't see this. This will happen every now and then. And like the spikes just comes, stays for about 2 seconds, and goes away all to one file. And the only way to handle that, like you can't QS that. That means dropping, right? The only way to handle it is have tons of 10 gig ports and serve the traffic. Now the good thing is it's easy to serve because it comes out of L3 cache. God, I wish people would display. We do some stuff for Debian, for security to Debian updates. And there's a lot of cron jobs that do apt-get updates on the hour, every hour. I'm pretty sure you can look at some of these charts we have and like pick out on the hour, every 5, every 10, every 15, just by the difference of the spikes. So if people are still deploying 1 gig, that's another area where you can get a good speed up by just going to 10 gig. And again, QS doesn't work. The solution is have bandwidth. 10 gig is cheap. If you ever think of buying a 1 gig switch again, just don't. Just buy the 10 gig. If you're stuck on Amazon, buy a bigger credit card and give it to Amazon. Because like your variability on a 1 gig link, you can saturate it so simply, right? One mistake, one bad query, one memcache key that grew a little bit too large very quickly because someone was appending to it, and your entire 1 gig network is down, right? And there's no QS that will help. So there's some interesting challenges with, I'm severely running out of time here, with 10 gig. But inside the network, you should probably be fine with them. These will be, yeah. So before I jump through to the last one, does anyone have any questions? Because we have about 3 minutes. Yes? Split brain? So it's basically 2 parts of the cluster that can't talk to each other. Or worst case, this part of the cluster can talk to this cluster part, but not this part, and this part can talk to some part here, but not there. And something you should design for, and something that in a competent network should very rarely happen. On the internet happens all the time. Any other questions? Okay. I'll go through this one. So, in a 10 gig network, and we're pushing 25 gig, or pushing 3 gigabytes per second. that is a lot of transfer that you need to keep in retransmission buffers. And so if you have a blip where the network goes away for 2 seconds, you now need 6 gigabytes of kernel memory available just for your retransmissions, which the kernel is not very good at. And we had this kernel bug that existed for a long time in the Linux kernel that we eventually helped track down, which was entirely latency dependent. So we ran this matrix of kernels in different locations to see which one would fail. And we couldn't find a pattern until we realized that geography mattered. Whatever kernel we put in San Jose or Amsterdam would crash within like 24 hours, and whatever kernel we put in Chicago did never crash. And why is that? So Chicago has the smallest catchment area of any of our POPs. And the bug was in the retransmission timer of the Linux kernel. So the more retransmissions you had, which is a function of the latency and the reliability of the links, the more likely it was to crash. So it took us about 2 months to track this one down. These are some syscontrols that you should set. Warning on the SYN backlog, if you set it 1 higher, it will go to 0 without a warning. And then I'll skip these. So, there we go. So one thing when you're moving to SSL that you should all be aware of is that when you send SSL packets, they're flagged as don't fragment. And carriers have these really shitty boxes that fuck with the MTUs. And so you might want to pull down MTUs when you do a lot of SSL to avoid the initial ICMP message back. We've noticed this a lot in the UK, for example, where all of Vodafone is 1/22, and all of Orange is 1/21 behind a massive carrier-grade NAT system. And you need to pull down the MTU quite a lot because of the shit they do. This is just a snippet from Bird, where you can do it per AS number, which is another example of why you want networking out of software, bad software, and into something that you can just hack on. Network hardware is a problem to overcome and thus never provide a solution, basically. So, again, questions? John, you must have some.
You really want to say that you have commodity hardware?
It is commodity. No, Bugatti is not commodity, but I would argue that something like, well, no, Bugatti is just Volkswagen, right? So yeah, it is commodity. You're right. You're right. See? It's just a function of larger DIMMs. It's what they did with the Bugatti. They took 2 V12s and put them next to each other. Yes. It's pretty insane, and a reason why you can't use Java. Because imagine that garbage collector stop while it scans 768 gigs of heap. Okay. Well, thank you, everyone.